In this video, we're going to look at the second option of the two approaches, and that is the Pucher-Douglas tool. As I mentioned at the beginning of the video for the area threshold flow network definition tool, we first need to develop a perennial stream network before we can begin citing conservation practices using the ACPF. And this is that three-step process where first we delineate a flow network. And like I mentioned, there are two different approaches, the area threshold method and Pucher-Douglas. Area threshold is an easily understood method and is repeatable due to the fact that the user gets to specify a certain threshold value, while Pucher-Douglas is objective and scientifically based, and the results are dependent on landscape characteristics as opposed to a user specification. Briefly, I'd like to make it clear what we mean by perennial stream network and also why we emphasize the importance of this. So to begin, a perennial stream network is one which flows continuously. You can see in the first hydrograph all throughout the water year, there is a base flow. There's a continual flow within that channel. In an intermittent or seasonal stream, flow is only going to occur at certain times of the year when it receives water from, say, springs or from other surface source, such as during like snow melt or something like that. You can see in the middle hydrograph, for the beginning of the water year, there is no flow, the base flow is 0, but then between January and June, there is some flow that's likely due to snow melt in that case. And then finally you can have an ephemeral stream, and this is the one that only flows in a direct response to precipitation, and whose channel is at all times above the water table, which we can see there in the last hydrograph, where there's just very sporadic flow occurring, most likely due to an intense rainstorm. However, for the purpose of the ACPF, we mostly want to be designating our stream network where we are going to be applying conservation practices down the road. For example, one of our last tools is a riparian assessment. So, if you are going to be interested in applying riparian buffers or other riparian practices to smaller, potentially intermittent streams, you may want to include certain streams. However, for the most part, people are generally only concerned with perennial, that is, continuously flowing streams. That is why we make this distinction here. The Pucher-Douglas tool works by using drop analysis to determine how high up in the watershed the stream network will be developed. Drop refers to the difference in elevation from the beginning to end of a stream segment, and drop analysis tests a series of thresholds to see which one meets the constant drop theorem. Now, the constant drop theorem determines if a mean stream drop of first-order streams are significantly different than the mean stream drop of higher-order streams, and this difference is tested with a t-test. If there is a significant difference, the constant drop law is not met, and a larger threshold is chosen until the law is met, defining the initiation point of streams. The constant drop theorem was developed by Brosco in the late 50s. And the concept is embedded in stream geomorphologic laws governing drainage network evolution. It makes sense, as first-order streams, which are higher up in the watershed, tend to have shorter lengths, but are associated with higher gradients, while higher-order streams, which are further down in the watershed, approaching the outlet, have longer lengths, but are along lower gradients, which you can see in the diagram above. Because of this concept, the Pucher-Douglas method may work better in well-organized dendritic networks compared to artificial or modified stream networks, such as where ditching has occurred. So we're back in our map document. We can see we have our area threshold network, which I'm going to turn off for now. And then we'll come over to our toolbox and go down to Pucher-Douglas and open it up. And we have 3 to 4 inputs that we can use. First required is our field DEM, our D8 flow direction roster, and then our watershed boundary. Optionally, you can include pour points if you have them.
And if you do, I highly recommend that you do include them. If you don't have any, this tool will automatically generate them as an optional output. And again, if you don't have pour points, I highly recommend that you do generate pour points. And then our final output will be the Pucher-Douglas flow network. So let's add our inputs. We'll come over and grab our filled DEM, drop that in. Our D8 flow direction roster and our watershed boundary are automatically added. I currently do not have any pour points, so I will automatically generate them. So I'm in my file geodatabase, right directory, and I'm going to name this pour points. And as always, I will end in my 12-digit HUC ID. Save. There we go. And then our Pucher-Douglas flow network was also automatically populated PD flownet, followed by that HUC12. And we hit OK and let it run. This tool uses Tau DEM, so it is going to run in the foreground, and while it's running in the foreground, you cannot do anything in your ArcMap document. If you're not familiar, a pour point is the outlet of a watershed, and it is very important to know what your pour point is. Everything upstream from a pour point will define a watershed, and each pour point will have its own watershed. So, if you were working with a non-headwater watershed, it'd be very important to define the input pour point and then the output pour point. In the Pucher-Douglas tool, if it's not provided, as you saw, pour points can be automatically generated. And this is done by extracting flow accumulation values that are along the watershed boundary. And the highest flow accumulation value that is at least 4 standard deviations above the mean will be selected and then converted into the point. So this means that we could get multiple outputs, and that's why we're going to review and edit our pour points once they are output. Here's an example of output pour points I got from a different watershed. You can see in yellow that 3 pour points were generated for this watershed along that boundary. And this is because we have 2 distinctive flow networks exiting the watershed at this point. In reality, the pour point should be put further downstream of the confluence of those 2 flow networks. So when we move it downstream, this will be considered our new outlet for the watershed. The tool is just finished running. You can see we have this completed. Everything was a wild success. So we can close this. And I'm going to add some color to make my flow network stand out. Make it pink. Now then I'm going to make my pour points large. I'll make them yellow. Okay. So the flow network looks fairly similar to what we got from area threshold. You can see, since I was able to specify a threshold with the other flow network, that it does extend further up. Based on that constant drop theorem, this is the initiation point for Pucher-Douglas, shown in pink. As stated before, this is an objective method, so based on the landscape, that was how that was determined. So let us take a look at our pour points now. And we can see that we got 4 pour points output. So what we're going to do is edit them to make sure that we are choosing the most downstream pour point and making sure that we only have 1. This watershed is a headwater watershed, so I don't have an inlet pour point. If you're working on a watershed that had the stream flowing into it from a more upstream watershed, then you would have an inlet point somewhere near the headwaters and an outlet pour point. But in this case, we only have our 1 pour point. So let's go ahead and edit it and choose the appropriate one. So I'm going to right click on pour points, edit features, start editing. Alright, and now we're in an editing session. And for one, I want to see where my current watershed boundary is. So I'll add some color to this to make it stand out real quick. Okay. And let me zoom in a little bit closer so we get an idea. So we can see right away that this most downstream one seems most suitable at the moment. And another valuable tool that we can use to figure out where to place our pour points is that flow accumulation roster. And you remember I thresholded mine to 1 acre of accumulated flow. That was 1,000 cells. So let's start editing. First off, I'm going to make this my only selectable layer, and that's just to ensure that I don't delete anything else that may be of value. So I can select and delete, and I'm just hitting the delete key. So we select and delete, and now let's zoom in. And what we're going to do is select this pour point and grab it and move it. And I'm going to move it as far as downstream as I can. So what's going on in this area is that there's a confluence. You can see it very clearly in the hillshade of 2 stream networks coming together to go into this larger river. And using the flow accumulation roster, I can see that point of confluence. So I'm going to move 1 cell upstream of the confluence. If I went at it or 1 stream below, or I'm sorry, 1 cell below, then this whole segment would also be included when I ran the Pucher-Douglas tool. And we're not looking for that. So I've gone 1 cell above the confluence, placed my pour point, looks good to me. So now I'm going to save my edits and stop editing. So now that we've edited our pour point and have it where we want it, we can rerun the Pucher-Douglas tool, throw in that filled DEM, and this time we can run with pour points provided using our pour points. And you can see it says this already exists. We know that, we just ran it. It's going to overwrite that output, and that's okay. So hit OK and let it run. Alright, so the tool is just finished running, and I just want to take a quick second to point out that when tools run in the foreground, this box that shows up is the same, or contains the same information that the results window contains. So here are the messages that are output as the tool is running, so you can see what it's doing, and you can see which inputs you provided when you ran this tool. For example, here we can see our pour points were included. That's also in the messages. So just in case you've never seen this before, it's the same thing as the results window. Alright, so let's close this, take a look at our results. Everything should be the same again, except for this time, down near our outlet. Since we moved that further downstream, we can see that the network actually does extend beyond our original watershed boundary to the actual outlet of this watershed, which this will be very helpful later on when we go to define our perennial network manually. Alright, and lastly, let's just take a quick look at that attribute table. And you will notice that it is the same as the area threshold was. And this will be very useful if we would like to grab segments from either network later on to use it to define our perennial network. There will be no issue appending them as they contain the same fields. And once again, we can see the stream type field that currently has all zeros. This will be the field that we are editing in the next video to create our perennial stream network. Here's a brief recap of everything we just went through. Next up, we get to code our perennial stream.